stuff. On Friday we talked about the law So, we talked about law of cosine. And in fairness, I gave you a pretty good one as our example, didn't I? One that was a little bit probably more painful than we would really like. So, we're going to talk about the law of sines today. And the law of sines is formulaically much easier. Like, really nice. But it's kind of like one of those things that is always really nice, but it doesn't always go. So, we'll show you the proof, I'll show you where this comes from, and then I got to show you why it gets so, let's go back to our triangle that we defined on Friday for the law of cosine. So, I'm going to do my axes here. And remember that I said that I had 3 points. And I pretty nicely said, well, I've got my 3 points here that are A, B, and C. These are limits here. So I say this is A, and then I kind of arbitrarily show B. And then from there, now, when we did that, we drew our lines here. Do that. And then we labeled our sides with the side, or excuse me, the angle opposite. So we said angle A projects on side A, angle C projects on side C, and angle B projects on side C. Alright, now, we said that there were some kind of things that we knew. We said that this was going to have swath. We said this, of course, was 0, 0. And then we said that this point was, well, I think I did it backwards. It was T0, but I think I put T in there. That's big T, actually. My spatial issues here, I apologize. Let's switch that. We'll make that. Okay? Alright. Now, much like we did Friday, I'm going to drop an out. Okay? Now, when I do that, there's something I can swap, there's something I can set. And that thing that I can set is that I'm a 90-degree angle. And I know that this height right here. Now, when we did law of cosine, we went through and did this formula also. Now, this is a lot easier. Yes. If I wanted to talk about sine of A, I know that that's just opposite of our bodies. So y. Right? And then if I wanted to talk about the sine C, well, I know that's just going to be A. Pretty cool. So, now, if I solve each of those for y, something kind of special happens. You'd say, well, this is actually y is equal to c times the sine of A. And then here, I can say that y is equal to a times c. And you should be kind of thinking that, oh, let's try to see where we're going with this. I've got y and y, I can just substitute in, right? So for primitivity, right, which is based on law of syllogism, that a is equal to b, b is equal to c, and a is equal to c. So I have c sine of a is equal to y, and y is equal to a sine of c. That is there. And if I wanted to group these, I can divide both sides by a, and sure enough, I'll get the sine of a over a is equal to sine c. And one of the things that's kind of exciting with that is if I put in an altitude from A here, what, right? So one of the terms that we use in multitude is let's say without loss of generality. And so that means that when we do it from one, we can in general explain it for all. And that's the law of sine. Formulaically, I would say sine of A over A is equal to sine B over B is equal to sine C. Of course, this is predicated on our setup here of side A being opposite. And side C opposite.
First it has like flip over, so that's 22.
Yeah, if they're reciprocals, then that's fine. I personally I like doing it this way, just because then I end up having not a mess on top on the way. But does it really matter? No. As long as you have that. The other big difference, honestly, is if I have something like this, I know it's going to be less than 1 over that, so it's usually the smaller numbers or less than 1. Whereas if I switched it, it would actually in a day and age where calculators doesn't make that much of a difference, when you're doing side rules, figuring it out by hand is a difference. Alright. Pretty slick. One thing. What is that? Right. When we talked about proofs of triangle trigonometry, way back in geometry, we said there were 5 general proofs of triangle trigonometry. The methodology, side, 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 angle, side, angle, side, angle. Right. Angle, angle, side, and then H. Right? So, we don't have an angle, side, side, chuckle, 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 or side, side, angle, but little does she know that's what we're talking about. Side, side angle is what we call the contiguous. Let's talk about what we mean. Let's say I gave you some information, and I said I want you to build a triangle. Let's say I gave you angle A, I gave you C, side C, and then I gave you side C. Now, let's take a look at what that means. So I've got just some sort of arbitrary number. And then I've got an inside. So I've got angle A. Now, let's say that A is smaller than C. Well, am I going to have a triangle there? Let's just kind of. So let's say side A, which we know is going to come from this piece, because we've got angle, side, and then side. If A is smaller than C, is it going to make a triangle? Not at all. So we know if A is smaller than C, we have F. Now, what happens if we get to a place where A is greater than C? Oh, part of it depends on how much, but do you have any information about how side A should fit in? So could I have a triangle that looks like this? Or could I also take this piece and swing it? So, does the law of sines work in all cases? There's certain places where we run into that. And that's when we see. So, we're going to do some examples of things that will work, and then I want to do some examples.